The way we write numbers, let's say a number 1428. Now this number actually comprises 4 digits, 1, 4, 2, 8, where we say that 8 is in ones place, 2 is in tens place, 4 is in hundreds place, and 1 is in thousands place. Right now, the point of saying that 8 is in ones place, 2 in tens, 4 in thousands, and 1 in 4 in hundreds, and 1 in thousands means that the number represented by these 4 digits is mathematically equivalent to 1 into 10 cube plus 4 into 10 squared plus 2 into 10 to the power 1 plus 8 into 10 to the power 0, which is 1. So you notice that there is 1000, there are 4 hundreds, there are 2 tens, and there are 8 ones, right? 10 to the power 0 is 1. Now, essentially what we are using, right, is base 10, right? In expressing the number 1428 in the base 10, right, we are using the what we call the decimal system. Now, decimal system of digital representation essentially uses the base 10, right? So any digits that you give me, I'll use the base 10 exactly like this. So the first digit to the right hand side, I'll multiply it with 10 to the power 0. The second digit from right, I'll multiply it with 10 to the power 1. Then the third digit gets multiplied by 10 squared, the fourth digit by 10 cube, and so on, right? So essentially, decimal system uses the base 10 in representation of digits, right? Now, if I want to change, right, if I want to change the system from base 10 to another, right, then how does this work? Now, let's take another example. Let's take the digits 1, 4, 3, 6. But this time, instead of these digits representing a number in decimal system, what if we use these digits to represent a number in the system that has base 7? Right, so notice that the way I write this representation is I bracket these digits, right, and I write base 7. So when I don't bracket these, the default base is 10. So conversion of this number, right, 1436 in the base system 7 to decimal should be fairly straightforward. Why? Because this number is equal to 1 into 7 to the power 3, just like we had 10 to the power 3 multiplying the fourth digit from right. We have 1 multiplied by 7 cube, then the next digit 4 gets multiplied by 7 squared, the next digit 3 gets multiplied by 7 to the power 1, and the last digit 6 gets multiplied by 7 to the power 0, right? So when I solve these, 7 cube, I have 343. 4 times 49 is 196. 3 times 7 is 21, and 6 into 1 is 6, right? So when I add these up, I get the number 566 in base 10, right? So 566 in the decimal system as we know it is actually equivalent to 1436 number in base 7, right? So we notice that conversion from another base to base 10 is fairly straightforward. But what if we are to convert a number given to us in decimal system into another system, right? So let's say we have to convert this number 566 back to base 7. So the way we do it is we write this number, right, inside a box like this. Okay, then let's start dividing 566 by 7, right, because we want to convert 566 in decimal to base 7. So 7 8 the 56 0, right? So 7 into 80 is 560, and we are left with a remainder 6, right? So we write 6 here. Then let's multiply this quotient by 7 again. So we get 7 1 the 7, 10, 7 1 the 7, and we are left with a remainder 3, right? Then we expand this and we multiply this quotient again by 7. So 7 1 the 7, and we are left with remainder 4, right? and we again divide this by 7. Now this time we get quotient 0 and remainder 1, right? Now as soon as you get the quotient 0, you got to stop, and these digits in this order, they are my number, right? So when I pick up this digit here, then the second digit 4, then the third digit 3, and the fourth digit 6, right? So I get 1436 in base 7 is equivalent to 566 to the base 10, right? So this is fairly straightforward. You just need to continue to divide until you get quotient 0. Now why don't we try another thing? Why don't we convert 566 into base 2? Right? Now base 2 is actually called binary, right? And all our computers and all, they're all using binary system, right? Binary system of numbers. So all computers are converting all of these numbers that we are keying into them into binary, and then doing their arithmetic on them. Now let's divide it by 2 to get our binary. So 2 the 4, 16, to 8 the 16, to 3 the 6. So there's no remainder, it gets divided completely, so 0. Then divide by 2 again, 2 1 4 1, and this time we have 1 remainder. Then 2 7 the 14, 0, 1 remainder. Then 2 35 and no remainder. Then 2 17, 1 remainder. Then 2 8, 1 remainder, right? Then 2 4 and no remainder. Then you have 2 2 and no remainder, and finally you have 2 1 and no remainder, right? And you have 2 0 and 1 remainder, right? So the number, let's start counting from here. So the number 1 0 0 0 1 1 0 1 1 0 to the base 2 is the binary representation of the number 1436 to the base 7 and equal to 566 in decimal. Right? So there is something very important that I want to now highlight here. Now when I started dividing this number 566 by 7, the remainders are the ones that the remainders left by this division by 7 will consolidate to become my number in the base 7, right? Similarly, when I started dividing by 2, all the remainders that I got by division by 2, right, you can look at this on this side, are the ones which got converted into the number in binary, right? Now isn't it interesting to see that the remainders will never be greater than or even equal to the base that is dividing this number, right? So in this case I would never get a remainder 7 or 8 or 9 or 10 and so on, right? Likewise, in this case I would never get, in case of binary, I would never get a remainder 2 3 4 5 and so on. I would always get remainder 0 and 1, right? So we can summarize that a base system will use digits from 0 to n minus 1, right? Where base system to the base n, right? So let's say if we have to convert some number into base 8, then this is going to use digits from 0 to 7 only, right? So these are again 8 digits but 0 to 7. Likewise, if let's say we were to use base 9, then this is going to use digits 0 to 8 only. A base 3 will use digits from 0 to 2 only, right? And so on. So until base 9 and 10, things are pretty straightforward because we have numbers as digits. But what if we were to convert a number into a base which is greater than 10? Let's take the example of number 25 in base 10, and let's convert it to a number of base, let's say 13. Right? Now to do this conversion, what we will need to do is we will start dividing 25 by 13, and 13 1 the 13, and we are left with 12 remainder, then 13 0 the and 1 remainder, right? So the remainders I have are 1 and 12. But if I have to write 1 and 12, right, to the base 13, this gives a completely different picture, because anybody can now mistake this number to be 2 into 13 to the power 0, 1 into 13 to the power 1 plus 1 into 13 square, right? Which is clearly not what I intended. This is clearly not what was intended, because this needs to be a single representation, right? This whole thing, this whole remainder needs to be a single representation, but I do not have any numerals, right, which will give me a single representation for 12. So I find a way out, right? So for as far as 0, 1, 2 and so on up to 9, these digits are concerned, I have no problem, I just use them straight away. But when the remainder is 10, now what I do is, the way out is I start to use the letter A, small a, right? For 11 I use the letter B, for 12 I use the letter C, and so on, right? So no matter what the base, I can continue to use A, B, C, D for 10, 11, 12, 13 and so on, right? So this gives me a single representation for the remainder. So actually 25 base 10 now becomes, so I pick 1 from here, so this becomes my tens place, and for 12 I write C. So 1C to the base 13 is equivalent to 25 to the base 10, right? So uh, any higher bases, I will find the conversions pretty straightforward when I start to use 0 to 9, then A, B, C, D and so on all the way until Z.